Yeah. Just a minute. Yeah. So today we'll be discussing the Mamba paper. So it is a very interesting recent development, and it has been pitched as an alternative to the transformer architecture. Yeah. So transformer architecture has few inherent problems. First one is the n square complexity when it comes to training, and if you use the right methods, um, the on complexity at inference time. Other thing that transformer fails is at very long sequences and being able to reason and find the relevant context at a very in different parts of the input. So Mamba tries to answer those things and trying to build something as a competition to transformer architecture, and later we will see how Mamba is able to get very good competitive performance to transformer architecture when it comes to inference speed and the perplexity of the model after fixed number of computations. So yeah, and Mamba starts from the idea of state selective state models, and we will cover them in detail. And it is not like a dense method like in transformers um, where we try to process the information present in the text through the interaction between the different dense vectors. And yeah, so to be able to understand Mamba, first we'll have to understand what are the state spaces models. So the format here is like we'll be referring to this paper and this notebook that I created, and we'll keep switching because there is a little bit of maths also here, and it's not easy to create a PPT with maths. Yeah. So to start with the idea with the paper, the authors mention that the efficacy of self-attention is attributed to its ability to route information densely within a context window, allowing it to model complex data. And we are aware of the performance of the transformer model across different modalities also. But these models, as I told earlier, have the n square complexity at training time, and they also, I mean, with the right positional embeddings and different types of positional information, we are seeing models that can go up to 128,000 tokens. But that is still a severe limitation, because with the adoption of LLMs, this boundary of context window needs to keep increasing, and later we'll see that Mamba models work up to context size of almost 1 million tokens also. So yeah, this is the starting point for the paper. So there are the types of most famous sequence to sequence models that we know are the first RN and LSTM type, where the competitions are recurrent. The best thing about RN and LSTM is that they can have an infinite context length, even though they don't really work well with very huge sequences. But still, in theory, you can have a very long context length on which the architecture can perform. But at the same time, they are not parallelizable, which makes their training very slow and not available for huge adoption by the industry. Transformers, on the other hand, they have a block-like structures where input is passed to each and every block, and you finally get the output. But they have a serious problem that they can only work on finite length, and as we discussed earlier, they have n square complexity. But a very good thing about them is that they are parallelizable, which means that you can throw a very huge amount of compute at them. And if you have huge compute and huge data, people are able to do a lot of good things with transformers across many modalities. But uh, but again, this n square problem is very central to the transformer architecture, and people have been looking for an alternative to this for quite some time now. So the starting point of Mamba is the state space sequence model, and we will see how they are a combination of both RNN and CNN. Specifically, they are a combination of recurrence behavior and convolutional behavior, and they are capable of long range dependencies. Originally, the state space sequence model, they didn't really work well with text because text contain a lot of dense information in their embeddings. But the way the contributions that the authors have given, and the model, the structured state space model that they are referring to, is able to work with text also, which we'll see later. So the main contributions of the paper are that they have added the, we will discuss this in detail, but just giving a high level overview. Originally, the state space model were time invariant. Basically, they behaved similarly for all the inputs irrespective of their time. So they gave these models the capability to recognize what kind of information is present at which token number. They have given very different hardware optimization algorithms which have allowed a fundamentally recurrent network to be able to be being parallelized on GPU. And again, these models, they can work with really long context. So let's start with the idea of state space model, which is present here in the paper. It involves a bit of math, and I've noted the math here so that we can understand it correctly. So a state space model is like a continuous system that maps an input to output using a latent state. This is the very basic definition. But the thing is that these models are present for continuous domains. So it's there like a function mapping a continuous variable from an input to an output. And these are how this is a continuous system which is represented this in this manner. So this is a differential equation which shows how the latent space, which is encoded as h of t, changes over time. And the output of the system yt is finally the latent space at that time multiplied by the matrix C, and the xt is the input to the system at that particular time, and the final output is the multiplication of latent vector with the C matrix, and and the input to the system multiplied by D matrix. As you can see, there are four variables involved in this system: A, B, C, and D. The authors have not used this term, and we'll discuss this later because it seems like a skip connection, which we'll discuss later. So, but as I just told that these equations refer to a continuous system. But if we are thinking of being able to work with text, we'll have to make the system into a discrete system so that uh, we can say, okay, at x equal to 1, we gave this input to the system, and at x equal to 2, we gave this input to the system. So to be able to do discretization of this system, we write the um what will we say this uh, the uh, shit, I'm not able to remember the word. Yeah, again, and the change in the latent.
Derivative. Derivative.
Yeah, derivative. Yeah, thanks. So we can write derivative in this manner also, right? For a very small, the idea is for a very small change, we can write the derivative like this. So what is the value of the latent space at t plus whatever the very small amount of time that is, minus the value at time t. So this derivative, then we can rewrite this entire thing like this. So at an additional time of delta, the value of this latent space can be written as this. And when we plug this value, the values for this equation here, we finally through these steps, we finally get this form here. So these matrices a bar is nothing but identity matrix plus the delta times A matrix, and B bar is the delta times the B matrix. So once we arrive to this formulation, we can rewrite the entire thing like this. Sorry. Yeah, we can rewrite the entire thing like this, where at time step t, the value of the latent space can be calculated through multiplication of the value of latent space at last time step times the a bar matrix plus the multiplication of b bar matrix with the input at timestamp t, and the output of the system is nothing but the multiplication of C matrix times the latent vector at time step t. So this is quite similar to the recurrent formulation that we see in RNNs also. So here the variables of the system are A bar, B bar, C, and delta. So since this is a very it's an approximation, these values will never give you the is not same as this equation here as a continuous function, but after discretization we can arrive a reasonable approximation of the system, and its parameters are again delta, a bar, b bar, and c, which are the parameters of the systems which we try to fine tune using backprop here, backprop and gradient descent. This has the recurrent formulation. If you remember the equations for RNN, they're quite similar like this. And interesting thing about this system is that the behavior of this system is encoded in these matrices A bar, B bar, and C. So they are not dependent on what is the input at time step t. The final output is dependent on the hidden state at that time, but these parameters are independent of the input at any timestamp t. So in a way this system behaves like in a similar way for all kinds of input. So that, which was a very serious drawback, because if they are not able to identify which kind of input is present at what time, they sometimes faltered in very complex reasoning tasks. So which is the solution that the authors have provided in this paper. So yeah, these are the equations that we end up deriving for the state space models. So this is a simpler derivation in the paper. They have not used Euler's method to arrive at those formulations. They have kept the a bar matrix as the exponent of delta times a, and they have come to it through a method called zero order hold. I don't know what this is, but yeah, instead of having these values for a bar and b bar, they have initialized through a different point from a different point. And yeah, so this is the system they are trying to work with. So here there is no multiplication of uh, yeah. Okay, it's ht minus 1, right? It's ht minus 1 here. It's not so basically it depends on the value of latent space at the last time step, and the value of input to the system at that time step, something like an RNN also, right? If you remember. So here the output depends on the hidden state value at the last time step, and the what the value to the system is at that particular time step. So y1 is basically, you can say, is a function of h and x, h naught and x1. I hope that answers your question. Okay, so this system has very interesting properties which make them yeah, we'll discuss those properties now. So these are the parameters of the system, original parameters. From a and b, we calculate the a bar and b bar. The thing is that to arrive at these parameters, there are two ways that we can calculate them. First one is a recurrence method, which we'll discuss, and the another one is a convolution method. So a recurrent point of view is like, let's say at h of -1 was 0. Okay, so the value for the first time step h0, based on these equations here, since ht -1 will start from 0, so h of 0 will be nothing but b bar times x naught, and y naught will be c times h naught. When we try to go to the next step, think of the unrolling method of RN and LSTM here. So it is the same concept, that we are unrolling in time gradually. So h1 will be a bar times h naught, and b bar times x1, and y1 would be c times h1. So at each time step, you keep getting the value of the hidden state variable, which you can use here. You will get the value of h1, which you will use here and in the next time step. So basically, unrolling in time at a single time step. So this is the recurrent view of trying to arrive at the values of at the output of this system. Yeah, a recurrent view of arriving at the output value of this system, which is quite similar to RNN. But again, this has a problem of slow training because we are doing it a single time step at a time. Another way, a very interesting way, is to use the convolutional mode, and which basically thinks of, okay, if you have the entire input sequence like this, right? You have x1, x2, x3, x4, all the way till xn. Why don't we pass this entire thing at a single time, just like we pass images to a convolutional network, to a CNN? Why don't we just do that? So it turns out that we can write these equations in a convolutional framework also. So yeah, basically here we were not expanding all these variables, right? We were not expanding what the internal values of h1 and h naught are, but in the convolutional point of view, we will end up expanding those values. So h naught is b bar x naught, y naught is c times h naught, so that is c times b bar x naught. For h1, we put the value of h naught here. So h naught is nothing but b bar x naught. Okay. Uh, for y1, yeah. For y1, we replace the value of h naught with that, and we get a term like this. And the thing is, if you keep doing this again and again, you will end up seeing an expression like this. So here you would see the for y2, it is c times a bar square times b bar into x naught plus c times a bar b bar and x1, and the final term of this is c times b bar x2. So this is a pattern which we can extrapolate and derive also for, let's say, a sequence of length k. For a sequence of length k, the final output, the yk of the system, can be written as c times a bar raised to the power k times b bar x naught. So for the first term, the a bar matrix will be multiplied k times, and with each increasing term, the exponent will keep on decreasing until for the final term there will be no a bar matrix multiplication. So we can think of this entire equation as a convolutional operation, which is nothing but a pointwise multiplication of two functions. So here we can come up with a k convolutional filter, which is nothing but c times a bar raised to the power k times b bar, basically all the coefficients that we see here. And at runtime, what we can do is we can do pointwise multiplication, like this term will be multiplied with x0, this term will be multiplied by x1, and In this way, if we have the entire input, we can pass the entire input in one go. But the catch is that we'll have to calculate all these value beforehand. And again, multiplying these value, like trying to find the kth power of a bar matrix is problematic. And they do this using Fourier transform. So this convolutional multiplication, they try to convert. So yeah, they find the Fourier of this individually, of both of them individually, and then they multiply them pointwise multiply, and then they take a Fourier transform of the entire thing. So we actually don't have to do the error prone calculation of matrix multiplication like a matrix raised to the power of k. So there are other methods also, just like Fourier transform that I just told, to be able to calculate this value. So it might seem daunting, but at training time, we can find this filter value for the operation. So how this system finally works is that at training time, they are going through this convolutional operations, like trying to, because at training time, we know the entire input sequence beforehand, right? So it makes sense to pass the entire thing at a single time to be able to train the system and find the value for these parameters here. And at inference time, they use the recurrent formulation. So let's say at inference time, they want to find what was the, just like how current transformer models also do inference, right? Given the present context, you will first predict the first token, and then you will predict the next token, like that. So this is how the state space models operate, and this is the system that on which these guys build upon. Any questions still here? Okay, I'll continue them. So so the theory that we discussed till now is the building block for the Mamba architecture. So if we can encode the interaction between the hidden states and the final output that we can get through those hidden states in this manner, we can train and do the inference from the system using convolutional and recurrent network. But this is all that we discussed till now is based on using a single dimension. Here x1 x0 is basically a scalar value. But what if we have n dimensions? Like if we have text, let's say we have 512 dimensions. In those case, they create this state space model, single state space model for each single dimension. So if there were 512 dimensions in the input, then they will have 512 different state space model for each of the dimension that is there. So for each dimension, there will be a separate y value also. So for dimension number 1, there will be y1, there will be dimension number 2, there will be y2, and then you'll have a final vector like this, which will have the final output dimension. Yeah. And again, this system, a very important variable in the system is this A matrix. Basically, you can think of A matrix as it keeps track of what information in the hidden state is important and might be useful for the future operations. So the way we initialize this A bar matrix is quite important, and there was a paper named Hippo which basically came up with a very interesting method to to initialize this A bar matrix so that it gives preference to the context which was near to the present token, and give less preference to the context which was quite far from the present token. So hippo initialization gave this system a very good performance boost on basic task also. Now, why do we need a Mamba here? So as I discussed earlier, the n square complexity is a problem with transformer. And how do we do good enough reasoning with the past context, for especially for very long sequences? And to highlight the need for Mamba, authors have picked up two tasks uh, which are quite interesting. First one is the task of selective copying. So if you see here, yeah. So in a normal system with let's say this input of these color inputs, uh, a normal state space model will be able to replicate the entire system, even if they are just separated in time. But if the task is a bit complex, where the there is white boxes between these colors, and uh, we want the final non-empty boxes as the output, then original state space model don't work here, because this thing needs complex reasoning, and as to be able to understand what is the empty box, or are we and at training time being able to understand that we are only interested in the colored box. So this is a mode of much more complex reasoning that the normal state space model fail at. Another problem is the idea of induction heads. So basically being able to understand, okay, if in the input we saw this block after a black block, so at runtime, at inference time, what output should follow a black block? So these kind of operations, they need they need to be they need to be able to understand what was the input to the system. The current state space models, they are independent of the variables for state space model. Like all these variables are independent of x and xt, which is the input at the time step t. So how do we the authors were thinking that if they give these state space model the ability to understand what input was given to them at what time, then these models could can do much more complex reasoning. Yeah, so for context aware reasoning, the model has to remember what was the input at what position. So to understand the algorithmic difference between the two approaches, the original parameters here, right? So here B is for batch size, L is for the sequence length, and D is the dimension. And all the parameters were independent of the sequence length. So the sequence length will basically show at what token position what was present. So all A, B, C, and delta parameters are independent of the L parameter. What the authors have suggested is encoding this positional information also in the system. So instead of keeping randomly initializing B and just using it, they use this SB matrix, which basically does a linear transformation of the original B matrix into B, L, and N. So all these parameters are now dependent on the positional information, on the sequence length. And this is a very stark difference to the previous state space model, because it comes at a very big cost. The previous state space model were time invariant basically, in that method we can apply both the recurrent formulation and convolutional inference, or sorry, convolutional training, because the system was time invariant. Now the system is time varying, so we can't have the convolutional approach of faster training here. We'll have to come up with alternatives that allow the system to to do faster training. Yeah. as recurrence only structure makes training way slower, and this is where major contributions of the paper are present. So the three main contributions of the paper for the increasing the training efficiency are parallel scans, hardware optimization, and recomputation. We will discuss what all these are. So this is a complex part of the presentation, so feel free to ask questions. The idea is that first we have to understand the GPU memory structure. So inside GPU, we have a slow inference part, a slow memory part where basically you can keep the entire model. And then this parts of these model which are needed for computation are passed to this faster power component of the GPU, which is called the SRAM. And S from variables from SRAM. SRAM is not in the size of GBs; it's mostly in the size of MBs or so. And um, the rest of the model, which is usually in GBs, is present in the slower part of the GPU. So the variables that are present in the SRAM, then those variables are then used to do computations. So the idea is that to reduce the training time, which would basically involve a lot of copy paste operations from this low speed areas to the high speed areas of the GPU. They keep the trainable parameters, the most important parameters of the system, on the high speed part of the GPU. So the idea is that whenever they need to do a computation on these or using these parameters, they don't have to leave the fast parts of the GPU. And so all the computational steps that are happening here on these parameters are being done on the SRAM itself with custom kernel ops. So they have written their own kernel operations. So traditionally, if we had, let's say, an addition operation and a multiplication operation, what would happen is, like, first you will retrieve the tensor to SRAM, do the addition, keep it back, and then bring it back from multiplication, and then bring keep it back. So when you write custom kernels, you can basically combine these addition and multiplication operations at the single time. So we keep these parameters on the high speed part of the GPU. We write custom kernel operations. So this itself gives a huge boost to how fast you can process these systems, even with their recurrent structure. The other idea is that they use is the idea of selection mechanism or scans. So we know that since we are in a recurrent formulation, the hidden state at timestamp one, to calculate that, we'll have to calculate the hidden state at timestamp zero. And to calculate hidden state at timestamp two, you need to find what are the hidden state value as timestamp zero and one. So if we have, let's say, six states like this, then we'll to do this operation, we'll have to do 1 plus 2 plus to the plus 6, which will be 21 operations. What they try to do is that they internally paralyze this whole thing so that these computations are not repeated again and again. And let's say if you are trying to do this with three threads, I might be wrong in this calculation, but instead of 21 operations, they might need only two operations. So basically, finding these recurrent values, they try to optimize it by forcing a parallel structure on it and using custom code to be able to find these hidden state values very efficiently. Yeah, and they also introduce specific kernel ops to avoid copying, which we discussed here, like restricting the amount of transfer of tensors that is happening within the GPU. And also, very interesting thing that they do is, like, for back propagation, you have to keep a lot of intermediate values on. You have to save a lot of those values so that back propagation can be done easily. But here they find that it is much easier for them to recalculate values for backprop rather than trying to store it in a tensor, because every time they do a move operation or move or copy operation, they that is the most time consuming part of the entire path, entire process. So they what they did is basically this recurrent operation, right? They just optimized it a lot using using tips and using different tricks, and they optimized it so much that we will later compare the inference speed, and we'll see that it does very well as compared to the transformer also when it comes to inference speed. Yeah. So yeah, the three important contributions were kernel fusion, parallel scan, and recomputation, which we just discussed right now. And now the final architecture that they have suggested. So their architecture is a lot like a block architecture that we have in transformers. So each of their cell, so there will be another block here, another block here. So uh, output of one block is the input to the other block, and this keeps on going. And just like transformers, they have multiple blocks stacked on top of each other. This is the design of a single cell that is inside the Mamba architecture. So these operations are linear projections, and they're basically increasing the dimensions of the operations that are happening here. So let's say if the input was 512 here, it becomes 1024 here. This is a skip connection. Basically, these are the main operations that are happening in the cell, and after the operation we add the skip connection value here, and then we when then we reduce the dimension again. So if here it was 1024, we bring it back to 512. Now to discuss about the operations here. So first they do a convolutional operation, not the convolutional operation that we have been discussing. it's uh, it is something like they're trying to mix the information between different dimensions, or else, as we know, for n dimensions there will be n different state space models. So they're trying to build get some sort of overlap between these different dimensions so that the model can come up with more complex reasoning. So this convolution operation does that. These are gating mechanisms. If I'm right, they are using CLU operation. I don't know what that is. And this is the SSM block, this one that we have discussed till now. Sorry, this one here, this operation, which finally gives the output, which is then passed to the block which is on top of the current block. And yeah, so the idea is that you take let's say 10 blocks of this architecture, you do the similar kind of training, and using backprop and gradient descent, you find the value for these parameters. And yeah, uh, these models are then able to they're able to find properties within sequences, and they are able to yeah uh, do good or perform well on long sequences also. And now we will discuss the result of this architecture, like how the experimental studies have turned out and what are the results of the architecture. So for the selective copying task, the one which we will be discussed here with the individual spaces between blocks, the Mamba architecture is very good at that, 99.8. And the original state space architecture was very bad, 56.4 accuracy. So S6 here basically means selective selection. Selective selection is here your this part, yeah, where you are adding when you're transforming these values to include the context length dimension also. This is the S4 and this is the S6. So basically S4 plus selection mechanism. So the Mamba architecture does really well for the selective copying problem. And for the induction head, you can see for even for sequence length of almost a million, the Mamba is performing, giving almost 100% accuracy. So you can say, okay, these tasks are what they started with, so they'll obviously be doing very well on them. What about other problems? Just give me a minute. Oh, there are so questions here. I have not seen their code repo right now, but I am assuming that they might be using fast Fourier transform. I will link this blog post, which was very helpful to understand, and they have written accompanied the entire code for S4 and S6 models, so that you can get an intuition of how that works. Uh, yeah, so A bar calculation by itself is not problematic, but if you're trying to do, let's say, A bar times K raised to the power K, so that involves a lot of operations back to back, like trying to multiply a lot of times. So the complexity of that operation itself is quite high and error prone also. Okay. So now let's compare Mamba architecture with transformers. So for transformers, they have used this term transformer plus plus, which is basically all the best features that are there in the Palm and Llama architectures. Rotary embeddings, Swiglu, MLP, RMS norm instead of layer norm, all the different, basically the best version of transformer architecture that is out there. And if you see the performance here, Mamba scales better than all the attention-free models and is the first one to match the performance of a very strong Transformer++. So if you see here, this shows the total amount of operations that are used for training, which is in flops, and the perplexity. So the idea is that with more and more flops, the perplexity of the system should go down. And if you compare the performance of Mamba and Transformer++ when it comes to the perplexity is quite similar. So it in one way you can understand perplexity, since the perplexity is quite similar, then they're basically understanding the same amount of information about the text. And this is for the sequence length of 2048, and for sequence length of 8192, which is here we can see that the Mamba is performing better than Transformer++ also. It is getting a lower perplexity with it achieves a lower perplexity before with using lesser number of operations. So I'm not sure which data set they have used here for training, uh, but yeah, it is interesting to see this. And again, for zero shot evaluations, uh, so here they are comparing with different open source language models, which are trained up to 300 billion tokens, 300 billion tokens, and they are trying to keep the model size quite similar here. So they're not trying to compare Mamba with, let's say, a GPT-4 sized model. Yeah. So these are the different categories. They, after fine tuning this model on, to up to 300, sorry, pre-training them with 300 billion tokens, they're comparing them with different zero shot evaluations on different tasks. It's like Hella Swag and Vino Grande. And yeah, Mamba here consistently outperforms the models in its class size, because we can't literally compare uh, a 1.4 billion Mamba model with, let's say, 100 billion any LLM model. But it would be interesting to see when we increase the size of Mamba architecture to a large number of parameters, how close does it come to a model like GPT-3 or GPT 3.5? That would be an interesting thing to see. and also just trying to implement Mamba architecture on different use cases also, like on different types of tasks like summarization or on QA, and just see how well do they generalize on a lot of things. So here they are showing zero shot evaluations after pre-training, and Mamba usually does better when compared to models in its own class size. And so here is the interesting thing that they show about very long sequences. So trying to the yeah. So with very long sequence length, we see that it is not comparing here with the transformer architecture, because I don't know if a million size transformer architecture would require a lot of memory. Yeah, but again, for huge sequence length, the you can see other systems, the perplexity is going up or staying constant, but Mamba's perplexity keeps going down. Um, and again with the classification, it's a DNA classification task, and the perplexity, so the accuracy of the system is for Mamba is continuously very good for even for a million tokens. So a million tokens is of a lot of information, and Mamba is able to do well on those tasks. And talking about efficiency, so in training, their efficient scan, basically this operation here, this operation on trying to find all the intermediate hidden states for each of the input token, um, using their efficient scan is 40x faster than standard implementation, standard recurrent implementation. And right, uh, as a recurrent model, Mamba can achieve 5x throughput than transformers, which is interesting, quite which is quite fast. And it is quite possible that someone might figure out the same kind of operations for even transformer architecture or for even LSTM. So just to speed their training and their inference also. And yeah, that's it from my side. Um, any questions?
So what? Hey, in your opinion, Akasha, what do you think is the downside for this algorithm? There must be some downside. Otherwise, why it's not becoming prevailing? Maybe it needs some time or what?
Yeah, it's quite new. It was introduced last December only. And
Mm.
the thing is, it requires very high custom kernel codes, very highly efficient. And I think not everyone can write that. Transformers operations are not, you can write them in Python, you can deploy them using C++ and all different other methods, but you're not, an average person is not writing kernel operations for transformer. So I think that might be a reason why it is not being immediately used by a lot of people. And yeah, I think it will take some time, because as I said, we people have to check, we'll have to do a lot of observation studies and comparative studies on different aspects of the different aspects and performance of the model. And I think it, I mean, the intuition and the zeitgeist around it is very encouraging, so I think people will experiment a lot.
Okay, thank you guys. I need to drop off. So thank you. I need to drop off now. Thank you.